One small step for man, one giant leap for mankind.
Named after the Roman god of travellers, Mercury is the first planet from the Sun. On its surface, the Sun appears more than 3 times larger in the sky than it is when viewed from Earth. Being the closest planet to the Sun, you would think it would be the hottest planet in the solar system. Well, it isn't. That title is held by Venus, but I will explain why this is in the next episode when we take a closer look at the second planet from the Sun. That said, Mercury's temperature and radiation levels are not suitable for life as we know it, and so we are extremely confident we would not find anything there resembling a life form. Temperatures on Mercury rise to 430 degrees Celsius on the surface during the day, and at night, without an atmosphere to keep the heat in, temperatures can drop as low as minus 170 degrees, which means Mercury has the most extreme temperature swing of any planet in the solar system. Being a third the size of the Earth, Mercury is the smallest planet in the solar system at 3,032 miles or 4,880 kilometres wide, which isn't that much wider than Australia. Mercury is also the densest of all the planets, with a huge iron core, some of which may very well be liquid or what we call molten. The core represents around 70% of Mercury's diameter. Earth's iron core, for comparison, makes up 50% of its diameter. In relation to its size, Mercury has the largest core of any planet, and, like Earth, it also has a rocky mantle and a solid crust. Mercury's surface is the most cratered of any object in the whole of the solar system. It sits at 29 million miles, or 46 million kilometres away from the Sun at its closest point in orbit, and 43 million miles, or 70 million kilometres away at its furthest, making it the craziest elliptical, or egg-shaped, orbit of any planet. Mercury orbits the Sun at 29 miles, or 48 kilometres per second, making it by far the fastest orbiting planet in the solar system, completing one orbit every 88 Earth days. Compare that to Earth's 12.5 miles or 30 kilometres per second with a 365-day orbit. Now, Mercury needs to orbit at this breakneck speed or it will simply fall into the Sun. It's a straightforward balancing act between momentum and doom, and it applies to all objects under gravitational influence. You may have witnessed similar yourself if you have ever watched a motorcycle on a racetrack or on a fast road whilst cornering. The rider leans the motorcycle over into the corner to make the bike turn. If the bike was to slow too much or stop, it would simply fall over, as gravity does its thing. But if the motorcycle maintains momentum, it counteracts the gravitational effect and continues safely on its way. It works in exactly the same way for Mercury. If it slowed too much, it would fall headlong into the Sun. There are no seasons on Mercury because the planet's wobble on its axis is as small as 2 degrees, which means it rotates with stability and almost completely upright at all times. Earth's wobble, again in comparison, is between 22.1 and 24.5 degrees. And this is what gives us the 4 seasons, something Mercury simply doesn't have. Neither does it have any moons or rings. It takes sunlight 3.2 seconds to travel from the Sun to the surface of the planet. And once again, in comparison, it takes sunlight 8 whole minutes to reach the Earth. Mercury has the wispy remnants of an atmosphere, primarily helium, plus a few other elements, and a strange lopsided magnetic field, just 1% of that, of the Earth's own magnetic field. Also, its day is twice as long as its year. I'll say that again. Mercury's day is twice as long as its year, rotating on its axis 3 times for every 2 trips around the Sun. You would rationally think if it rotates on its axis 3 times, that would equate to 3 days, as it does on Earth. 2 trips around the Sun would be 2 years. You'd be right about the years, but for the 3 days, not so fast. That isn't the case. To help you make sense of that, allow me to say this. The sun has to go from directly overhead of a given point on a planet to directly overhead to the same point again to complete a solar day. And that does not happen on Mercury, just because it has rotated once on its axis, whereas on Earth that is almost exactly the case. Just in case you didn't know, one full rotation of a planet is known as a sidereal day. So to reiterate, a solar day is where the sun goes from directly overhead to directly overhead, and a sidereal day is when a planet completes a full rotation on its axis. A solar day on Mercury takes 176 Earth days, and one sidereal day takes 59 Earth days. For us on Earth, one solar day is almost the same as its sidereal day, give or take a few minutes, as the sun goes from, again, directly overhead to directly overhead in almost the same 24-hour period it takes our planet to rotate on its axis. Let's look at exploration of Mercury. The Mariner 10 spacecraft passed by Mercury 3 times in 1974 and 75, taking nearly 3,000 pictures of the surface from as close as 200 miles away. Unfortunately, it was the same, lit by the sun's side of the planet on all 3 occasions, and so the spacecraft only managed to gather information from a relatively small part of the planet. But it was a start. The spacecraft was the first to use a flyby of another planet, in this case Venus, to alter its trajectory, using the gravity of the planet, which would give a slight tug on the spacecraft and promote the change of direction required. In March 2011, the Messenger probe became the first spacecraft to enter into orbit around Mercury, unlike Mariner 10, which didn't enter into orbit, but instead completed 3 flybys on its way around the Sun. Mariner 10 is likely still orbiting the Sun too. To enter orbit around Mercury is tremendously difficult and a much harder feat to accomplish than it would be with any other planet. Firstly, you have to slow the craft down enough, which takes a lot of fuel and costs a lot of money, not to mention that the extra fuel takes up a lot of room on the spacecraft, meaning you need to add more fuel just to lift the extra weight of the fuel required for slowing down once you get there, to get the spacecraft off the ground back here on Earth and up into space. Also, if the spacecraft fails to slow down enough on approach to the first planet, then nothing can stop it from plummeting directly into the Sun due to the enormous gravitational pull. As you approach the Sun, your speed increases as its gravity pulls you in, and so you need to fight against that, and that would take lots and lots of fuel. Now, Messenger did something completely different, and NASA scientists came up with a near 8 billion mile trajectory that would keep the spacecraft out of the clutches of the Sun, and it wasn't expensive compared to the other option. Taking over 6.5 years and many circuits of the Sun to get there, Messenger's mission began with a takeoff from Cape Canaveral in August 2004. Using Earth, Venus and Mercury itself to alter its trajectory, and later using Venus and Mercury again a number of times to reduce its speed, as each planetary flyby would create a tug on Messenger and either change its direction, as I explained earlier, or slow it down, just enough with little help from the spacecraft's rocket engines as it neared the planet on final approach, for it to then fall into Mercury's gravitational hands, where it gathered tons of data and went on to map the whole planet. Messenger discovered that, very early in the history of the solar system, Mercury was impacted by a massive space rock. It hit so hard it created huge protruding ridges perfectly opposite the impact site, known as the Caloris Basin, on the other side of the planet. Messenger, using spectroscopy and photography, studied the entire surface of the planet, and to scientists' surprise, due to the planet's proximity to the Sun, discovered water ice in deep craters at the planet's poles, places the savage heat of direct sunlight simply could not get to. Messenger also discovered the elements sulfur, phosphorus and potassium folded into its rocks. Now, if Mercury had formed in its current orbit, then the Sun would almost certainly have vaporized these volatile elements. And so the conclusion we are left with is, well, Mercury must have formed further away from where it now resides, possibly even further out than the orbit of Mars, and if so, it wouldn't be too far of a stretch to suggest it was given a gravitational nudge inward by the gas giant Jupiter billions of years ago. Gravity can interact with that of another body in two ways. It can either attract or, depending on proximity, distance, trajectory, the path the bodies are taking, and the speed of the body, actually repel. The larger body with the larger mass generally dictates the outcome and would hold its own position more or less, basically bullying the much smaller object and sending it packing. Now, somewhere along its way inward towards the Sun, Mercury almost certainly had a collision with another object and had most of its surface removed, and more so, this collision may well have been responsible for Mercury's wild elliptical orbital path around the Sun. By 2015, Messenger had run out of fuel and, on the 30th of April, it crashed down onto the planet's surface, adding one more crater to the pock-marked Mercury.
That's one small